HTML, and then everything. It needs me to sync it because it's not correct.
Excellent staffing, by the way. I like that.
Great. So, sort of overview of the type of ways we have dealing with, or some of the ways we have dealing with these large data intractabilities. So those intractabilities border out by the fact that things are polynomial. The other intractability I hinted at in my talk earlier, one of the main ways we have of dealing with that is these non-Gaussian likelihoods. And one of the main ways, as I mentioned earlier, we have of dealing with that with expectation propagation. So Ricardo is going to tell us about that.
Is it working? Okay. Talk to you about expectation propagation. Non-Gaussian likelihoods, and was slightly introduced in the morning. And I will introduce a sparse variant. Problem, at least most of the about today and yesterday, they Latin variable, and that Latin variable is that variable. So in this case, this would be like a noise around it, and what we observe is this sensible to think that this is a this is giving us the mean of the process controlled by this parameter sigma squared. And making this noise Gaussian will be Gaussian, and we have a with a very large data set. We will find problems. Assumption in the likelihood is not longer adequate, and we can process cannot be Latin variable, but the noise or the is just inside certain interval. Try to control that with the variance. You can try to make we have a different likelihood and model it this way. A binary classification problem. We want to model binary probability, and variable has values in a very different interval. Process and force it to be between so that solves the problem with the likelihood, but that is really tricky, solving this integral. Well, we can, but not exactly. TI factors to have P is just some constant to make this that try to match and make this as and the notation will anyone sees something weird and wants me to clarify. So in this particular case we are choosing each TI and conveniently we will choose this TI unnormalized. They will be proportional, but these are which makes sense because that's the event we are. So approximation that is Gaussianly distributed. Is approximates its TI sequential approximation to that one, and then we'll move to another one. So if we were working on the approximation factors, if we are interested in analyzing here for this element, and then we just get some marginal distribution. Gets out of the integral because and well, this is the definition of the cavity distribution. The divergence between these two. TI are Gaussian. So we are interested that this mu I hat is equal we do that, then we will find the distribution on this side. We also need and then we do that. This set will help us find this over. So suppose we have this our likelihood, some so if we make the product of these two terms, I hope you can see this, the blue line. This blue line. We are finding an element that is Gaussian. But we are finding the elements the new these elements. So it's so the prediction is elements we have just optimized with EP. That will be the variance. Is the distribution of another. So we will still find to find we still some sort of quadrature. Now I just give one example. I'm just putting random points in the place if in the place there are and what I'm going to but there are more than 100 speakers of native language. Something it's, I mean, just finding a nice to find people speaking native language. The complexity of this algorithm is cubic. Let's compute. Can apply the same sparse And there are two algorithms that has this extra term. And I don't know if it makes much sense to repeat. Later download the slides. And well, FITSI. So it's faster. To apply this DTC approximation directly. Because terms will tend to become really small. Problem. But we can embed the just that James also mentioned. Very similar to FITSI. It's complicated than if we try to do that. What we get is something like this, which is also very similar. Now, this trace term is helping us to now we are saying our approximation to the approximation. If this go very large, then our likelihood, and we want to optimize this lower bound. Going far away from where we have no data. Maybe I use to identify where the two clusters are. I have gone too fast.
I think it's the same term. But it had a sigma squared on the outside. Ricardo introduced this sigma tilde term. Instead of one sigma squared for everything, every data point now has its variance, and that's arising from the local approximation made by those site parameters. So this actually weights this trace term. So if one of these variances is very large because it's inverse, this component of the trace term disappears. But if the variance is small, the component of the trace term is switched in. That's sort of what happens with EP, that you can get this weight. Now, the way EP works is if you're the variances are very large. You get this added effect in here that instead of these close to where the decision boundaries are, where you're most uncertain. Variational DTC, it happens more. 5, this one's on a contour of about 0.6. They never sit, because actually this one is reasonably certain. The reason is going back to the previous slide, because in the probability it becomes very confident. Thing weights things up. So just point that out.
So, yeah, if we use the standard DTC, have this. So yeah, these points will just go far. The other thing, James. So.
Does it depend critically on where you've sampled your data, because you've not got much coverage in the bottom right there with your in the lower right,
yeah,
you've got some distribution.
So it's sort of decided that it's just noise.
What I wanted to see.
Yeah,
that's
so no inducing points there. So yeah, that's a problem with the lack.
See, that's because it considers that they are needed. And that's the tricky part when we optimize these kind of models, because in some cases the inducing inputs can be, where you place them can be quite important. So yeah, this sparse approximation is just missing, it's not sure what's going on, so it's going to 50-50, and this one is considered important to place up inducing input there.
And that's very common with FITC. If it gets to a region where things seem to get a bit complicated, it sort of has this ability to just give up. And the way it gives up is it just removes inducing points away from there, and everything just becomes noise. The sparse variational DTC isn't quite allowed to give up as easily because of the penalty term. And it doesn't actually have the ability to increase. It's to do with this weird heteroscedastic effect you get in FITC.
Something else that I have noticed with FITC is that it seems to have less points here, right? It seems that we are using less using inputs than here. But the thing is that it's, in some cases, it's just placing one on top of the other, which is redundant. Might be my implementation, but yeah. James was mentioning when he optimized the when we optimize this sparse variational approximation, we can optimize altogether the parameter, the kernel parameters, and the location of the inducing inputs. In EP, that is different, because well, we can optimize the location and the parameters, but at some point we are adding one middle step, which is doing the likelihood approximation. So to optimize a model that is using EP, we will need to do several steps. So we approximate the likelihood EP, then we optimize the parameters, and then if we approximate again the likelihood, we will get something different. So we can keep doing that for a while, and then at some point that might converge. So that's something worth trying. It's not only using EP and optimizing, it's better to have several loops. Now EP can be tricky because it depends on the likelihood we are using, and it's not certain that it would always converge. There are other algorithms or other variants of EP, some called the double loop EP, and others that force EP to converge. But I'm just introducing the standard, well, the standard plus the variationals. But if you are interested in EP, there's lots of things to read and different ways to implement it. And if you want to go to some references, well, there's a Minka introducing the EP. Again, this is the this is generalized FITSI when Naish Guzman and Holden introduces the FITSI variant for EP. And well, there are the unifying view of sparse approximations, where you can see about DTC, FITSI, PITSI, and many others. And it's just for the sparse variational approach, and of course Christopher Williams and Klaus Rasmussen. So for EPs, has a very good explanation in this book. Any more question?
Questions for Ricardo, or also questions about anything you've heard this morning? People are hungry. They're worried that lunch disappeared quickly last time, so I'm just going to start walking towards the... No. What we'll try and do again is, what time will be scheduled to do the be back into the lab class? 1:30. So if you could try and make sure, where's Genuino, the server's up. So the servers are up. Hopefully you've got your piece of paper from last time. So by 1:30, if you can be in here, logged into the server and ready to go. I think if you look online, you'll see that the instructions for the second lab, it's the same page as last.